All right, so the next thing that we're going to talk about is Archimedes Principle. So what is Archimedes Principle? Let me explain that. Suppose you have a container with water, okay, and you have an object. For simplicity, let's just assume that the object is shaped like a cylinder, though the same principle applies to any shape of an object. It's a little bit easier to think of if it has a regular shape. And let's say that you weigh the object in air, right? To weigh the object, let's use a spring balance. So what is a spring balance? A spring balance is just a spring which is with a scale next to it. Okay, and then you attach something to the spring, and from the scale you can measure how much the spring is extending, right? You know that for a spring, the force on the spring is k times x, where k is the spring constant, x is the amount that the spring has stretched. So if the spring constant is known, by measuring how much the spring has stretched, you can easily figure out what is the force that's stretching the spring, and hence you know the weight of the object. It's the weight that's stretching the spring, so you can find out the weight of the object. So that is the principle of a spring balance. So let's say that you use, so this is a spring balance. If we were having this class, having this discussion in class, I could have easily shown you a spring balance. We have a lot of those in the storage room. So suppose you measure the weight of an object using a spring balance by suspending it from a spring balance. And then you measure the weight of the same object by after immersing it in water. Same object, same cylindrical object, after immersing it in water, you measure its weight with the spring balance. Which case would the weight be greater? If you think about it a little bit, even if you don't have any experience with this subject, you will probably guess correctly that the weight is greater in air. So let's call this the weight in air. And let's, so I'll just write it's the result of what the measurement with the spring balance. What the spring balance is measuring is the weight in air, and what the spring balance is measuring here is let's call that W water, the weight when it's fully immersed in water. So the weight in air will be greater than the weight in water. Why is that? The reason is because when it's immersed in water, there are two forces acting on it. One is the weight of the object, which is acting down. That's mg, right? And then there is also a buoyant force acting on the object, which is pushing it upwards. Why is there a buoyant force? Okay, I'll talk about that in a moment, but you can see that if there are two forces, there is an upward force in addition to its weight, then its effective weight would be lower. Its weight would be, the spring balance would measure mg minus fb. So weight in water would be mg minus the buoyant force, and that's why it would be less than the weight in air, right? All right, now let's talk about this buoyant force. Where does this buoyant force come from, and why is there a buoyant force? Why is it upwards? To understand that, the easiest way to understand that is to just think in terms of a regular shaped object. That's why I made our object regular shaped, though the same logic applies if the object is not regular shaped. Let's say that the area of the object is A, cross-sectional area. Notice that the upper face of the object is encountering a pressure P1, and the lower face of the object is encountering a pressure P2, right? So the force due to the water on the upper face is going to be, remember the formula for pressure, formula that contains connects force, pressure, and area. Force is equal to pressure multiplied by P1 multiplied by the area. And the force on the bottom face is going to be P2 multiplied by area. Now you know that P2 is greater than P1 because it's at a greater depth, so there will be more force on the bottom face than on the top face. And so there will be a net force due to the water in the upward direction, and that is the buoyant force. That is the origin of the buoyant force. So it originates from the fact that when an object is submerged, there is more pressure underneath the object than there is above the object, and so there is a net force in the upward direction. Okay. Archimedes principle allows us to calculate this buoyant force, right? So what does Archimedes principle say? Archimedes principle says the following, and he gives us a practical way of calculating the buoyant force. Suppose you take a beaker which is filled to the brim with water, right? And suppose you take an object, like in this diagram I have a stone, and you gently lower it into the beaker, and so that causes some water to overflow, because as you know, fluids are incompressible. So if you are putting something into the beaker, it's not possible for water to squeeze and make room. So some water has to exit the beaker, and that's why the water is going to overflow. And it's going to contain, and let's say that you are collecting every drop of water that's overflowing. And so you've collected all the overflowed water, all the displaced water in this other container. Now, Archimedes says that if you weigh the displaced water, the weight of the displaced water is going to be exactly equal to the buoyant force felt by the stone. Okay? So Archimedes principle says that buoyant force is equal to the weight of the fluid displaced. That is Archimedes principle. Now it turns out that we don't need to actually do this experiment of putting of filling up a beaker with water and then collecting all the displaced water. We don't really need to do it, because we can actually go ahead and calculate the buoyant force just from that idea. So here is our container full of water. We have lowered a stone into the container, and we want to calculate the buoyant force on this stone. According to Archimedes, the buoyant force is equal to the weight of the fluid displaced. Now, can you tell me what is the volume of the weight of the fluid displaced? Or what volume of water, or how many cubic centimeters of water is this stone going to displace? Remember that fluids are incompressible. So if this stone has a volume of 27 cubic centimeters, for example, then exactly 27 cubic centimeters of water has to get out in order to make room for it, because it's not possible for water to squeeze and make room for it, right? Fluids are incompressible. So the volume of fluid displaced is exactly equal to the volume of the object submerged. Volume of the object submerged. So in this case, in this particular example, the entire volume of the object is submerged. And so if the volume of the object is V, then the volume of the fluid displaced is just the volume of the object V, right? Now, what is the weight of V cubic centimeters or cubic meters of water? To find that, you would just use the density of water. We are going to use this very important relationship that density is mass divided by volume. We are going to use this relationship a lot in this chapter. So the mass of fluid displaced, we already have the volume of the fluid displaced, would be volume multiplied by the density of the fluid, right? And so the weight of the fluid displaced would be equal to mass times g, so V rho F multiplied by g. And according to Archimedes, that is the buoyant force. So we have found a formula for the buoyant force. The buoyant force on an object is equal to the volume submerged multiplied by the density of the fluid multiplied by g. It's very, very important to pay attention to two things in this formula. Number one, what is the V? V is not necessarily the volume of the object. It is the volume submerged. So if the entire object is submerged, then it would be equal to the volume of the object. But suppose the object is a ping pong ball that's floating in the water, then only a small part of the object is underwater. So in that case, you would just use the volume of the object that's submerged, right? So that's V in this formula. And what about the density? Note that the density is not the density of the object, it is the density of the fluid in which the object is submerged. So the buoyant force has nothing to do with the density of the object. It depends entirely on how much of the object is submerged, what is the density of the fluid. These are the only two things that the buoyant force depends on. So this is a very, very important formula. That's the formula for the buoyant force. Now I must go back to my original example and clarify one thing. We talked about the weight of an object in air and the weight of an object in water. We talked about how the weight in water would be less than the weight in air because underwater there is a buoyant force which pushes upwards. Now I must also clarify here that there is a buoyant force in air as well, right? So there is. So when you're measuring it when you're measuring the weight in air, you are actually measuring the same thing, the true weight of the object, and there is also a buoyant force in air. However, the buoyant force in air, the formula for that we just learned is V rho g. The rho that you should be using is the density of air, right? The density of air is very, very small. It's about 1.29 kgs per meter cubed. So this buoyant force in air is actually very small, and so that's why we usually ignore it. But it's good to keep in mind that whenever an object is immersed in a fluid, there is always a buoyant force. So there's a buoyant force in air which is very small because of the density of air being small. So it's usually it does not really significantly affect the weight of an object. But if the object is submerged in something that has a higher density like water, then the buoyant force can be significant. Okay. Alright, so this is the point that I made earlier, that buoyancy is independent of the material submerged, and also the formula for the buoyant force is V rho F g. So it does not depend how deep in the fluid the object is submerged. The assumption is that the density of the fluid does not change with depth. However, that is not strictly true. If you like, the density of ocean water at the bottom of the ocean is a little bit higher than the density of water at the top of the ocean. But we are ignoring that. So if you just assume that the density of water is constant, which it is for most practical purposes, then the buoyant force does not depend on how deep an object is submerged. It's the same FB whether it's submerged near the surface or whether it's submerged at the bottom of a lake. Okay. All right, let's look at an example problem. So I'll let you read this problem first, and then let's give it a try. So a solid object with density rho is held completely submerged in a liquid with density rho f well below the surface. When the object is released, what will it do and what acceleration will it have? That's part A. So we have this container, and inside this container we have submerged an object with density rho, and the density of the fluid is rho f. Okay, what will the object do if rho is greater than rho f? So rho is equal to 2 times rho f. So the density of the object is greater than the density of the fluid, right? So all that we need to do is consider the forces on the object. So this analysis is very similar to Newton's second law analysis that we did in chapters 4 and 5, except that the only new thing is that there's the buoyant force, which is a new force. But everything else is pretty much exactly what we did in chapters 4 and 5. So what are the two forces on the object? There is mg acting down. There is the buoyant force Fb acting upwards, right? So whichever of these two forces is greater will determine the acceleration of the object. So mg, in this chapter we will use, as I told you earlier, in this chapter we'll tend to use volume times density for mass a lot. So the weight of the object, let's just call that Fg. It's probably better to call it the gravitational force rather than m times g in this chapter. So the gravitational force would be equal to mg, which is volume of the object multiplied by the density of the object times g, right? And what about the buoyant force? Buoyant force would be equal to the volume submerged multiplied by the density of the fluid multiplied by g. So that is going to be the volume of the object, because the whole thing is submerged, multiplied by the density of the fluid multiplied by g. So you can clearly see that Fg will be greater than Fb, right? And so the object will accelerate. So the net force will be in the downward direction. Net force and the acceleration will be in the downward direction. And so if you just let the object go, it will start sinking downwards. So this object will sink. And what acceleration will it have? That's just a Newton's second law question. The acceleration is net force divided by mass. And I'm just doing the magnitude of the acceleration because we already know that it's downwards. So the net force would be V rho g minus V rho Fg divided by the mass of the object, V rho g. We can express everything in terms of one of these densities. So we can just get rid of, we can use the fact that we can express everything in terms of either rho or rho f. The problem hasn't specified which one. So let's just express everything in terms of the density of the fluid. So we'll just plug in 2 rho is equal to 2 rho f. So 2 rho f multiplied by Vg minus V rho F G divided by V times 2 rho F G. This should be a G. All right, so a lot of stuff cancels out. Oh, there shouldn't be a G over here. So it's mass, so it's just V times rho. So the V cancels out, and V cancels out, and what are we left with? 2 rho F minus rho F. So that's just rho F divided by 2 rho F. So also the rho F cancels out. So we are just left with 1/2 G. 2 minus 1 divided by 2, which is just 1/2. So it's G over 2 in this example. So the object will sink downwards with an acceleration of G over 2. Okay. Part B is asking what happens if rho is equal to rho F. So if rho is equal to rho F, we know what Fg is and Fb is. So if the rho and the rho F are the same, then Fb and Fg are going to be the same. If rho F is equal to rho, right? Which means that the net force on the object as it's submerged is going to be 0. So the object will just stay where it is. If you leave it, there's no net force on it, so it will just stay where it is. You can move it and place it over here if you like, but again, when you let it go, it will just stay there. So the object will just be in equilibrium, right? It won't have any tendency to either go up or go down. All right. Now, this condition, when the buoyant force is equal to the gravitational force, is called the condition of flotation. So flotation, an object is said to be floating when its buoyant force and gravitational force are exactly the same, and it does not necessarily mean the object has to float with a part of it sticking outside. That's what we normally think of as floating, when a part of it is sticking outside. But flotation really means that the buoyant force and the gravitational force are equal. And so this is one example of flotation, right? Whenever the buoyant force equals the gravitational force. All right, now what will the object do? So part C, what will the object do if the density of the object is less than the density of the fluid, right? So going back to our diagram over here, which you've seen many times now, we again have the gravitational force and we have the buoyant force. The gravitational force is given by V times rho times G. The buoyant force is given by V times rho F multiplied by G. So if rho is less than rho F, then the buoyant force will exceed the gravitational force. And so the object will have a tendency to rise towards the surface. So in this case, the object will float up. It will rise towards the surface, right? What will its acceleration be? You can easily find the net force, just like we did for part A. You can easily find the net force, divide by the mass, and you will find the acceleration. So I'll let you do that yourself. All right, now let's consider the other case. What would happen when it reaches the surface? Let's consider the second part of part C. So what's going to happen when it reaches the surface? It has an upward acceleration. So when it reaches the surface, it's going to penetrate the surface and part of it is going to come out, right? But remember that the buoyant force depends on how much is submerged. So the moment a part of it sticks out of the water, it's not getting any buoyant force. The buoyant force only applies to the part that's submerged. So the moment it starts poking out of the water, the buoyant force will start going down, right? And at one point, it will stick out of the water enough that the buoyant force has reduced and gone down to what its weight was. So in the end, the situation will be like this. Here is our object. A part of the object is now sticking out of the water, and only the submerged part here determines the buoyant force. Only this part determines the buoyant force. So that's less than, so the buoyant force is less than what it was in the previous part of C when the whole object was submerged, right? So this reduced buoyant force would equal the weight of the object, and the object would just remain in this situation with a part of it sticking out. So when the buoyant force equals Fg, the object will be in equilibrium again. So it will just continue to float. It will continue to float with a part of it sticking out. Now we can easily calculate what part of it would be sticking out. So let's quickly do that calculation. So suppose the volume that's submerged is little v. Let little v be the volume submerged. We know that Fb is equal to Fg, right? So Fb would now be volume submerged times the density of the fluid multiplied by g, and that should be equal to the weight of the object, which has not changed. It's just the mass, v times rho is the mass multiplied by g. So from here you can solve for the ratio little v divided by capital V, and you can see that it is equal to the density of the fluid, the density of the object divided by the density of the fluid. In this particular example, this ratio is 0.9. It's given in the problem. So you can see from here that the volume submerged is going to be 90% of the volume of the object, and 10% of the volume of the object will be sticking out, right? So yeah, so whenever you have an object that's floating partially submerged, the part that's submerged is given by the ratio of the density of the object to the density of the fluid. One interesting application of this is ice. So ice has a density of something like that. I think it's 920 or something like that. It's approximately 90% of the density of water. So ice is a solid, but it has a lower density than its liquid form, water, right? So if you look at a piece of ice and if you put it in water, you will see that it floats with most of its volume submerged. And now you know that the volume that's sticking outside the water is going to be about 10% of the volume of the ice, of the piece of ice, right? An interesting application of that is icebergs. So and icebergs used to be a major concern for ships once. So here's my ship, okay. So you might be on a ship and you might find that there is a giant iceberg sticking out of the water. And some of these icebergs can be huge. They might look like mountains. However, you know that what you can see sticking out of the water is only 10% of the volume of the iceberg. 90% lies underneath the surface. And so even though the iceberg might look like it's a few miles away, it might be right next. The part of the iceberg might be right where you are, and the ship might easily ram into it. Nowadays, it's not so much of an issue because most ships have sonar, and so you're always using ultrasound to monitor the surroundings. But in the old days, this was a major concern. Okay, and that is in fact how the Titanic sank. All right. So the important takeaway from this slide is that the density of the fluid versus the density of the object immersed in the fluid. I have a little typo in my PowerPoint. I'll fix that after I record this lecture. It says model rho L versus rho S. So what I meant there is rho versus rho F. So I'll fix that. So the density of the fluid versus density of the solid, fluid versus density of the object, determines whether an object will float or sink. There are many practical applications of this. So one question that you can easily answer now is one that you might have thought of as a kid. So if you take a little pebble and you put it in water, it immediately sinks, right? But consider a giant ship, an aircraft carrier, which has like which has thousands of people, tens of fighter jets. It's like a mini floating city, and football fields, vehicles. How does that stay afloat, whereas a tiny pebble will sink? Now you can answer that question. What determines whether an object will float or sink is the average density of the object, which would simply be rho, or mass, divided by the volume of the object. So how this number compares with rho F, the density of the fluid, is what determines whether the object will float or sink. So for a ship or a boat, it's made into a shape such that its volume is much greater. Its volume is very large. So if you take the mass of the ship divided by its volume, what you get is a small number, much smaller number than if you had just taken a piece of iron of the same material and divided its mass by its volume. Then you would have gotten the density of iron, which is much greater than the density of water. But if you beat the iron into the shape of a boat or a ship, and then do mass divided by volume, you're going to get a number which is much smaller, because now you've made the volume much larger, right? So the average density of the object is much lower, and the density of water is 1000 kgs per meter cubed. So if you take mass divided by volume for this boat, it's going to come to about 1000 kgs per meter cubed, and that's why a ship or a boat floats. Okay. What about a submarine? So a submarine can decide whether it wants to float or sink very easily. Just imagine that this circle represents a submarine which is coming out of the board, right? So we are seeing a cross section of the submarine. Submarines have ballast tanks. Which kind of look like this. So these ballast tanks can be opened or closed. If the ballast tanks are opened, then the submarine fills up with water, seawater. So these ballast tanks, if these valves are opened, I mean, these ballast tanks get filled with water. And what does that do? The average density of the submarine is the mass divided by the volume, right? So if a large part of the volume is now filled with water, the effective volume of the submarine is lowered, right? So mass divided by volume, this ratio goes up, and so the submarine will sink, right? If the submarine wants to float up, then all it needs to do is use compressed air to push the water out and empty the ballast tanks. And so in that case, the volume of the submarine goes up, effective volume of the submarine goes up, and the density goes down, and the submarine floats up. So that's another application. How does a life jacket work? So a life jacket, um, when you inflate the life jacket, you are increasing your effective volume, because so again, think in terms of mass over volume. So you are increasing your volume a lot by inflating the life jacket. You're increasing your mass by a small amount because air has a very low density. So filling up the life jacket with air hardly increases your mass at all, just increases your mass negligibly, but it increases your volume tremendously, right? And so your mass divided by volume ratio goes down, and so your effective density is lower, and that is why you can very easily float. Your effective density just has to be less than the density of water. Another application is in the Dead Sea. It's very easy to float. So if you just lie down in the water in the Dead Sea, you will find that you have no trouble floating at all. Why is that? Because the density of the water in the Dead Sea is higher than the average density of water. The average density of people, since we are mostly made up of fluids, the average density of human beings is very close to the density of water. For some people, it's a little higher than the density of water. For some people, it's naturally a little lower than the density of water. So that is why some people have no problem floating in water anyway, without any effort. Other people have a hard time floating in water, and they tend to naturally sink. So, but for most people, the density of their average density is fairly close to the density of water. The density of water in the Dead Sea is much higher, and so most people have no problem floating in the Dead Sea at all. Okay, so these are some applications of the fact that the average density of an object determines whether it will float or sink. All right, now Archimedes' principle is so called because, as you probably guessed, it was discovered by uh, one of the brightest, one of the smartest human beings of all times, Archimedes. Um, Legend has it that the king of Syracuse in Greece had this problem. So he loved, uh, he had a huge collection of crowns, and he wanted his crowns to be made of pure gold. Now, he was suspecting that some of the artisans who would build his elaborate and very, very intricate crowns were skimming some of the gold. Right? So they could easily replace some of the gold with bronze or something, and paint it over with gold, and hide the painted bronze deep inside the crown. Uh, Even if they could steal a morsel of gold from here and there, uh, they could get very rich because gold is extremely valuable. So, and then it would be impossible for the king to figure out whether a particular crown has a little bit of gold replaced by gold painted bronze or something. So he wanted Archimedes to come up with a way of figuring out whether a crown was pure gold or whether it had something else mixed in it. And this was a very complicated problem, because you do have to find a very difficult problem, I mean, because what you really need to do is compare the density of the crown with the density of pure gold, right? But there was no simple way of finding the density of the crown, because density is mass divided by volume. How are you going to find the volume of the crown? So the crown does not have any simple shapes. So how would you find the volume of the crown? So legend has it that Archimedes thought about this problem for a while and could not make any progress on it at all, until one day he lay down in his bath, and he watched the water rise in the bath as he was sinking into the water. And that is when he had an epiphany, and the solution to this entire problem came to him. The legend has it that he even forgot to put on his clothes. He was so excited, he just started running through the streets of Syracuse shouting, "Eureka, Eureka." Eureka means I found it. So what was the solution that Archimedes came up with? All right, so let's say that the weight of the crown in air, let's call that WA. Yeah, so the weight of the crown in air, which is something that's easy to measure with a spring balance, is WA. And so WA, you know, is V times rho times G. And this rho is the average density of the crown, so let's just call that rho C. Rho C is the density of the crown. Okay. Now suppose you weigh the crown in water. So this is weight in water, a terrible notation, but okay. Weight in water. That is going to be less than the weight in air. Why? Because there is a buoyant force, right? So the weight in water would just be the weight in air minus the buoyant force. Okay, so from the second equation, you can rewrite the second equation and write weight in air minus weight in water is equal to the buoyant force. This just followed from here. All right. So the weight in air is something that you can very easily measure. Weight in water also you can very easily measure using a spring. You can measure both of these using a spring balance. Take this equation, let's call this equation number 1, and this equation, let's call this equation number 2. And let's also write down the formula for the buoyant force. So I'll just do that first and then name it equation 2. So WA minus W water is equal to the buoyant force. The buoyant force, since the entire crown is submerged in water, is just going to be a volume of the crown times density of water. I'm just going to call that rho for the day. I'll rho water times G. Okay, let's call this equation our equation number 2. Now let's divide equation number 1 by equation number 2. We'll divide the left sides, we'll divide the right sides. What does that give us? Weight of the crown in air divided by weight of the crown in air minus weight of the crown in water. If you divide the two right sides, the V and the G cancel out and you get rho of the crown, which is what you were after, divided by rho of water, which was very well known at the time of Archimedes. People did know the density of water. And so magically almost you have found the density of the crown in terms of very easily measurable formulas. Weight in water divided by the density of water. This was Archimedes' stroke of genius. He was a very, very, very brilliant person. This is just one of the things that he discovered. There is many, many other things that he discovered as well, which are insanely brilliant. But this is a very, very simple way of finding the density of any object of any complicated shape. All you have to do is use a spring balance to get its weight in air, then get it submerged in water, get its weight in water. Weight in air divided by weight in air minus weight in water. That number multiplied by the density of water will give you the density of the object. So this method is used a lot. It's called Archimedes weighing. It's used a lot in finding the densities of objects which are extremely brittle, like dinosaur bones. And also, it's one of the accurate methods of finding the body fat percentage. So athletes are often, so if you want to find the precise fat percentage in the body of an athlete, what you need is you need a very accurate measurement of the density of the athlete, right? And that's one step, and then from there you can figure out how much of that, how much of the athlete's body is fat, how much of it is muscle, and how much of it is bone, and so on. How do you get that very accurate measurement of the density of the athlete? What's done is the athlete is weighed in air, and then the athlete is asked to lie down in a tank filled with water and weighed at and the bottom of the tank is a scale, and so the athlete is weighed underwater, and then using this formula you can find the average density of the athlete. All right. I have an example problem on slide 19, which you can try. Okay, the next thing that we're going to talk about is this conceptual question. So I'll let you think about this question. At what point in an object can the entire buoyant force of the object be considered to be acting? So what does that mean? So you know that you can consider the gravitational force to be acting at the center of gravity of an object, right? The buoyant force is, in reality, it's acting on every particle of the object, but what is one point in the object where you can consider the buoyant force to be acting? Like if you were to think of the buoyant force as a single force acting at one point on the object, where would that point be? So would it be at the center of gravity of the object? Would it be at the center of mass of the object? We talked about how for regular sized objects, the center of mass and center of gravity are pretty much the same point. So is it answer choice C? Most people choose one of A, B, or C when I ask this in class. The correct answer is none of these. So let me explain why that is the case. Okay, it's very simple if you think about it. So here is a container which has some water, and let me put an object inside this container. Let's say that the object is a composite rod. Half of it is made of iron and the other half is very light. So the right half is made of iron, it's heavy. The left half is made up of, let's say it's made of plastic, it's very light. Where is the center of mass of this object going to be? It's clearly going to be in the iron side, maybe somewhere over here, because the iron side is heavier. So this is the center of mass. Where is the force of gravity going to act? The force of gravity, you know that the center of mass and center of gravity are pretty much the same point. So the force of gravity would be acting at the center of gravity, which is pretty much the same as the center of mass. So the gravitational force would be acting over here. Now, where is the buoyant force going to act? Well, think about Archimedes Principle. Archimedes Principle says that the buoyant force is the weight of an equal volume of water, right? So consider a rod which is entirely made up of water. Just imagine this same shape entirely filled with water, entirely made up of water, right? Archimedes' principle says that the buoyant force is equal to the weight of an equal volume of water. Where would the weight of the water act? It would act at the center of mass of the water. This is the weight of the equal volume of water. And that is the buoyant force. So where would the buoyant force act? It would just act at the geometrical center of the object. So FB would act like this. So the buoyant force, so our very important takeaway from here is that the buoyant force acts at the geometrical center of the object. Okay. It does not act at the center of gravity or center of mass of the object. It acts at the geometrical center of the object. Okay. This has many consequences. Suppose you have, consider a ship, and let's say the ship is coming out of the page, and so we are looking at a cross section of the ship, right? Okay, suppose the center of mass of the ship is over here, and the geometrical center of the ship is over here. So this is the center of mass, and this is the geometrical center. I'll just call this geometrical center. Okay, what would happen to this ship if it were slightly tilted? So suppose this ship tilts a little bit. The center of mass is right here. The geometrical center is right here. Let's think about all the forces acting on the ship. So the gravitational force is acting downwards through the center of mass. The buoyant force is acting upwards through the geometrical center, right? So if you consider a point somewhere over here, what kind of torque are the two forces applying relative to our point? So the gravitational force is trying to rotate the ship in the, let's call this the point O. Gravitational force is trying to rotate the ship in the counterclockwise direction, and the buoyant force is also trying to rotate the ship in the counterclockwise direction relative to the point O, right? And so what's going to happen to the ship? The ship will try to rotate, the two forces will exert a combined torque which will try to bring the ship back. It will rotate the ship in the counterclockwise direction and make the ship vertical, which is exactly what we want. So here you have a restoring torque, which means that this equilibrium that we have with Fg acting down and Fp acting up, is it a stable or an unstable equilibrium? If you have a restoring torque, it's clearly a stable equilibrium, and so it's going to be hard to topple this ship. So if a wave tilts the ship, if a large wave tilts the ship a little bit, there will be a restoring torque which brings the ship back. So this is good. However, suppose you have a ship like this. What's going on? You have a ship like this. The center of gravity for some reason is higher, and the geometrical center of the ship, or let's say that the center of gravity is higher, the geometrical center of the ship is over here. So center of gravity is here, center of mass is over here, and the geometrical center is over here. Now this ship can be in equilibrium, right? So the gravitational force could equal the buoyant force, so it could satisfy the condition of flotation, and it could float, right? However, what would happen if this ship tilts? Let's draw that. The center of mass is way higher over here, so the gravitational force will be acting down like this, and the buoyant force would be acting up like this. Consider a point in between these two, somewhere over here. What kind of torque are the two forces applying in this case? The gravitational force is exerting a clockwise torque about the point O. The buoyant force is exerting a clockwise torque also about the point O. So the two forces are together applying a net clockwise torque, which is clearly very bad for the ship. It'll make the ship completely tilt over. So this is an unstable equilibrium. So this one was a stable equilibrium, and this is an unstable equilibrium. So this shows you that since the buoyant force acts through the geometrical center of an object, it is very important that in designing a ship, the center of gravity of the ship be below the geometrical center of the ship. So the mass distribution of the ship should be such that its center of gravity is below the geometrical center of the ship. This has an interesting historical application. This fact was not known. People have been building ships since the beginning of time. This fact was not known even during the Middle Ages. So at that time, people would build ships, very big ships, and then they would put a lot of stuff on the ships. Like they would put these extraordinarily heavy guns on the ship, pack as many of them as they could fit there. Then they would build these lavish living quarters on the ship. So as a result of putting all this stuff on top of the ship, the center of mass of the ship would keep rising higher, because if you pile more and more mass at the top, then the center of mass keeps rising, and it's quite possible that the center of mass of the ship would be higher than the geometrical center of the ship's structure. And so in that case, you would build this ship, but then it would be in unstable equilibrium, and once it went out to sea, it could easily be knocked down by a strong wave. Okay, all right. I'll show you a demonstration of this fact, a little demonstration of this fact. Let's see if this video works. So loading a tractor on top of this raft will certainly raise the mass, the center of mass of the system higher than the geometrical center. And so you can see that this is unstable equilibrium. Okay. And it topples over. All right, so I have a problem based on the gravitational force versus the buoyant force. So you can just look at this on your own. And another word problem over here. Okay, and so that concludes our discussion of Archimedes' principle.